Researchers at the Massachusetts Institute of Technology may have just presented one of the most promising answers to humanity's escalating water scarcity. This innovative apparatus possesses the remarkable ability to extract pure, potable water directly from arid environments, operating entirely without electrical power, mechanical components, or any form of human intervention. Their groundbreaking invention, no larger than a typical window pane, has already undergone rigorous testing in one of the planet's most desiccated locales, demonstrating its efficacy in producing water under conditions where all currently available passive collection systems utterly fail. So, what principles govern its operation, and could it represent the future of autonomous water provision? Let us investigate. The concept of drawing moisture from the atmosphere is far from novel. Indeed, it ranks among the most ancient human technologies. Evidence of water collection from precipitation dates back to at least 2,000 years before the Common Era, when early civilizations ingeniously shaped stone formations into conduits to direct rainwater into subterranean reservoirs, capable of storing vast quantities of this invaluable resource. The Roman Empire further expanded this infrastructure across its vast territories, constructing aqueducts and collection networks of unparalleled grandeur and precision. However, rainfall is inherently a seasonal phenomenon, and in the most arid regions, where water security is paramount, precipitation is also the least dependable. Consequently, communities evolved to tap into a different source of water, not from the sky above, but from the air surrounding them. In the elevated regions of South America, the Inca people fashioned fabric screens to capture the dense fog that drifted in from the Pacific Ocean. Similarly, on the volcanic island of Lanzarote, agriculturists arranged fields of porous volcanic gravel to entrap overnight dew, which would then trickle down to nourish the roots of grapevines planted in the depressions at the center of each crater-like cultivation bed. Modern adaptations of these techniques remain in use today. In Morocco, the Dar-C Hamad project manages the world's largest fog harvesting network, utilizing over 6,500 square feet of mesh netting to extract more than 1,600 gallons of water daily from the Atlantic fog, thereby supplying 5 isolated Berber communities without the need for any mechanical assistance. In Chile's Atacama Desert, investigators have enhanced fog net coatings and their spatial arrangement to boost water yields by as much as 500%. And in Ethiopia and Cameroon, 30-foot bamboo structures, known as Warka water towers, leverage natural air currents and advanced materials to simultaneously collect rain, fog, and dew, yielding up to 26 gallons per day under optimal circumstances. Nevertheless, all these systems share a fundamental limitation. They necessitate a significant level of ambient humidity to function. When the air becomes dry, their water production ceases. Yet, it is precisely in the driest regions that communities face the most acute water stress. For the past 2 decades, engineers have striven to bridge this deficit through powered solutions. Atmospheric water generators, or AWGs, function by refrigerating air below its dew point to induce condensation, essentially operating as large-scale dehumidifiers. In warm, humid conditions, they can produce between 2.5 and 5 gallons of water per day for a single household. However, they consume between 0.5 and 1 kilowatt-hour of electricity for every quart of water generated. In regions lacking dependable electrical grids, which are invariably the areas most afflicted by water scarcity, these devices are not always a feasible option. But in June of 2025, Engineers at the Massachusetts Institute of Technology published findings on a novel device specifically engineered to address this gap. This passive water harvester operates effectively in desert air without requiring any electricity, moving parts, or external energy input beyond the daily solar cycle. The device is approximately the dimensions of a standard window, encompassing a total surface area of about 5.5 square feet. From the exterior, it appears as a sealed glass enclosure. Internally, suspended at its core is a sheet of specially engineered hydrogel, fashioned into a pattern of small domes reminiscent of bubble wrap. This increased surface area significantly enhances the volume of vapor the gel can absorb per unit of time. The hydrogel incorporates lithium chloride, a salt compound possessing an extraordinary affinity for atmospheric moisture. Lithium chloride extracts water vapor from the air even at humidity levels as low as 10%, a threshold well below that at which fog nets or dew collectors can operate. Previous hydrogel systems utilizing similar salts encountered a critical drawback. The salt would leach into the collected water, rendering it undrinkable without additional purification. The MIT team integrated glycerol into the gel's composition, which stabilizes the salt content and prevents its diffusion into the resultant water. Field trials confirmed that the water produced contained salt concentrations well within the acceptable limits for safe human consumption. Furthermore, its operation requires absolutely no human intervention. During the night, as temperatures decline and relative humidity marginally increases, the hydrogel absorbs moisture from the surrounding atmosphere. With the dawn and the subsequent rise in ambient temperature, the gel warms, contracts, and liberates the captured moisture as vapor within the enclosed glass chamber. The exterior surface of this glass is treated with a radiative cooling polymer, maintaining the glass surface at a temperature lower than that of the internal air. This thermal differential causes the liberated vapor to condense into liquid droplets on the interior surface of the glass. These droplets then flow down specially designed channels at the base of the apparatus, where they are collected as pure, drinkable water. This entire cycle repeats every 24 hours, necessitating no electricity, no batteries, no filters, and no ongoing human input beyond the initial placement of the device. The prototype underwent a week-long trial in Death Valley, California, experiencing some of the lowest ambient humidity levels found anywhere in North America. Throughout this testing period, the device functioned across relative humidity ranges from 21 to 88%, yielding between nearly 2 and 5.5 fluid ounces of water daily. On the driest days of testing, at humidity levels where all existing passive harvesting systems ceased to function, the MIT device persisted in producing water. It significantly outperformed fog nets, dew collectors, and even some powered AWG systems operating under comparable conditions. The MIT research group estimates that 8 panels of this size could adequately meet the daily drinking water needs of a single adult. An even larger configuration of panels could potentially supply an entire household's drinking water requirements with no recurring energy expenditure whatsoever. However, passive collection systems, such as these, represent a minuscule fraction of the methods currently employed for fresh water acquisition. Throughout the majority of the 20th century, the predominant strategy for addressing water scarcity involved the development of extensive infrastructure, including dams, reservoirs, aqueducts, and groundwater extraction facilities. These were engineering solutions designed to transport existing surface and subterranean water resources to areas of demand. They necessitated substantial capital investment, rendering them viable only in regions where governments or international bodies possessed the financial capacity and political will for their construction. Unfortunately, in the areas most severely affected by water stress, these prerequisites rarely coincided. As groundwater aquifers began to deplete, partly due to agriculture, which accounts for approximately 70% of global freshwater consumption, the focus shifted towards desalination and water recycling. While both technologies are effective, they also demand significant energy inputs and fixed infrastructure, thereby limiting their applicability to regions with stable power grids and capital for development. The water crisis is a progressively worsening global issue. Currently, over 2 billion individuals lack consistent access to clean, safe drinking water, a crisis that tragically claims more than 1 million lives annually. And while arid regions bear the brunt of this crisis, its impact is not confined to developing nations. In the United States today, 46 million people face water insecurity, and across Europe, 40% of the population is impacted by water scarcity. This situation is projected to deteriorate further. By 2030, experts anticipate that global groundwater demand will surpass supply by 40%. A contributing factor is that once reliable rain patterns are becoming increasingly erratic and unpredictable. But this is largely a self-inflicted problem. Primarily, unsustainable practices are the root cause driving this crisis in most regions. Agriculture and livestock alone account for nearly 70% of global freshwater usage, but when coupled with burgeoning populations and water-intensive industries, we are depleting rivers and aquifers at a rate exceeding nature's capacity for replenishment. This often leaves bottled water as the sole recourse in many areas, an option that is costly, unsustainable, and beyond the reach of those who need it most. The MIT device is presently a preliminary prototype and not yet available for commercial acquisition. However, it signifies a future where water procurement is not contingent on pumping, piping, or purchasing, but rather on its direct extraction from the atmosphere. The IIT team is just embarking on this journey. Cheng Lu, the lead author and now a professor at the National University of Singapore, states that the subsequent phase involves refining the material itself, optimizing it for enhanced yield, accelerated moisture release, and potentially more economical production. They are also developing a multi-panel array, interconnecting several harvesters into a vertical grid. This approach could escalate output from milliliters to liters, transforming the system from a survival contingency into a dependable daily water source. The next stage involves field trials in diverse climatic zones, ranging from humid jungles to coastal regions and arid plains. These evaluations will aid in fine-tuning the design, assessing long-term durability, and determining the optimal deployment strategies for large-scale implementation. However, for those seeking an immediate solution for off-grid and rural applications, passive fog collection systems remain the most viable option, provided one resides in a suitable climate. These systems are commercially accessible and have been proven in field applications across coastal desert environments for decades. A single 3-foot by 3-foot fog net panel in a humid coastal setting can collect between 3/4 of a gallon and 2.5 gallons of water per day, depending on prevailing conditions. These systems require no power No moving parts and minimal maintenance beyond occasional cleaning of the mesh surface. Material expenses for a do-it-yourself installation are less than $100 per panel. If you found this narrative engaging and are interested in learning about solutions for off-grid self-sufficiency, we invite you to explore our video on the Zirpot, Nigeria's ingenious off-grid refrigerator that has demonstrably saved thousands of lives.